Hello, and welcome to this presentation on the binomial series. There are many uses of the binomial theorem within the topic of algebra, for example, used in permutations, in combinations, and also used in probability. The theorem is also used in atomic physics and in financial mathematical calculations. Binomial theorem aids simplification of engineering proofs, theories, and practical problems. A binomial expression consists of two terms, for example 1 plus x, a plus b, 5y minus 2, 7x squared plus 6, 7a cubed plus 3b squared. They're all binomial expressions. The binomial series or binomial theorem is a formula for raising a binomial expression to any power without lengthy multiplication. The general binomial expansion of a plus x to the power n is convergent for all positive whole numbers of n, and is shown in the binomial series in equation 1. So here's our expansion, a plus x to the power n. The general series is a to the n plus n multiplied by a to the power of n minus 1 times x, plus n multiplied by, in brackets, n minus 1 multiplied by a to the power of n minus 2 multiplied by x squared, all divided by factorial 2, plus n multiplied by n minus 1 multiplied by n minus 2, a to the power of n minus 3 times x to the power of 3, and so it goes on to n multiplied by n minus 1 multiplied by n minus 2, n minus 3, a to the n minus 4, x to the 4 upon factorial 4, etc. Okay, so that is the general binomial series. Just a brief word about factorials. When you see 2 exclamation mark, 3 exclamation mark, 4 exclamation mark, it doesn't mean, as it would in normal English, 2, 3, 4. It doesn't mean shout them out. It means factorial 2, factorial 3, factorial 4, etc. Table below shows you factorials 1 through to factorial 6. Factorial 1 is equal to 1, factorial 2 is 2 times 1, so it's equal to 2, factorial 3 is 3 times 2 times 1, so it's equal to 6, factorial 4 is 4 times 3 times 2 times 1, so equal to 24, factorial 5, 5 times 4 times 3 times 2 times 1 equals 120, and so it goes on. Okay, on your calculator you will actually find a factorial key. It's often n exclamation mark, and the n is the number of the factorial. So if you want a 4 factorial, you'll put 4 and then press the n factorial key, and it will give you 24. I just repeated on this slide the a plus x to the n expansion for convenience here. Within this general expansion of a plus x to the power n, it can be seen that in, for example, the fifth term, so I'm talking 1, 2, 3, 4, in this term here, this is the fifth term in the series, that 4 is a common number. In other words, there are 4 n values here, n minus 1, n minus 2, n minus 3, that gives you 4 numbers there. We've got a to the power of n take away 4 multiplied by x to the power of 4 over factorial 4. So in the fifth term, 4 is a common number. If you looked at the sixth term, 5 would be a common number. And this is useful sometimes when we're looking for a specific term in a series, so we don't have to expand the full series. The rule is that for the rth term in a binomial expansion, it would be expected that the term r minus 1 is very important. So in the rth term of a binomial expansion, a plus x to the power n, we'd have n minus 1 in brackets times n minus 2 to r minus 1, and that will be a to the n take away r minus 1 x to the r minus 1 over r minus 1 factorial. That's just a very generic way of saying the above. We'll be using this principle in some of the questions we're going to look at when we just want to find one term in maybe a series that has 11 terms in it. Example A here, just showing us how to use the binomial series. It says, using the binomial series, we've got to find the expansion of x plus 4 squared. Now that's something we could do with our basic algebra, x plus 4 times x plus 4. We've all done those kinds of expansions before with your crab claw method or your smiley face method. But we're going to use the binomial expansion. One thing to note with binomial expansions, if the power, the n, in this case is 2, we will find there will be n plus 1 terms in the series. There will be 3 terms, in other words, in the series. So our expansion of a plus x to the n will look like this. A to the n plus n times a to the n minus 1 times x to the power 1 plus n times n minus 1 a to the power of n minus 2 x to 2 over factorial 2. We will have those 3 terms in the series. So notice in our particular case we're expanding x plus 4 squared. In this case then our a in our generic expansion is actually x, and the x in our generic expansion is actually 4. So be very careful of that. The n of course is 2, that's the power raising it to. So now we just simply put the values of a and x into our above equation. So x plus 4 squared can be written using the binomial series as x squared, which is the a to the n, so a is equal to x and n is equal to 2, plus n, which is 2, so I'm using this second term, 2 times a to the power, that would be x to the power of n take away 1, that's 2 take away 1 in this case, times by the value of x, so that's 4. Looking at my third term here, I will have n, which is 2, multiplied by n take away 1, so 2 take away 1 in the bracket, and then the a, which is x, raised to the power of n take away 2, so that's 2 take away 2, and the x, which is 4 in this case, squared, all over factorial 2, which is 1 times 2. On the next slide, I just simplified numerical values, so x squared is the first term, and I get 2 times 4, and the second term is going to be 8, and that's x to the power of 1, or simply x. And then for the third term here, I get 2 times 1 in the bracket, times x to the power of 0, because 2 take away 2 is 0, and that's times by 4 squared over factorial 2, which is 2. So simplifying my final line, I get x squared plus 8x plus 16. If you do the numbers on this, you'll get 16 for the last term. And that's what we would get if we expanded the x plus 4 times the x plus 4 at the beginning using our crab claw method. That's exactly the expansion we would have got. Example B here. Again, we're going to use the binomial series to expand the bracket 3x minus 2y raised to the power of 4. Now that is a more complicated expansion because that means that 3x minus 2y times 3x minus 2y times 3x minus 2y times 3x minus 2y. Now doing that algebraically with our traditional methods will be quite time consuming and we'll probably make a lot of mistakes in it. So it's easier to use the binomial expansion, binomial series in this case. So don't forget, if n is equal to 4, the power is 4 in this question, then we'll have n plus 1 terms in our series. We'll have 5 terms in the series. And that's what I've got here, 5 terms in my series. So that's the a plus x to the n binomial expansion. Now again, be very careful. The a in our case will be 3x. The x in our case will be minus 2y. So again, be very careful with the way you extract your numbers. We've got 3x minus 2y in our bracket. The first term is an a, so a is 3x. The second term is the x, and that's minus 2y in this case. And the n power is 4. All we do now is put those numbers into the above binomial expansion. So here on the first term, I'm going to get the a to the power n, so that will be 3x, which is my a, to the power of n, which is 4 in this case. Looking at my second term, I then plus the n, which is 4, multiplied by the a, which is 3x raised to the power of n minus 1, that's 4 minus 1. And that's multiplied by x, which is minus 2y. Again, please make sure you use brackets in the appropriate places here. It's essential to have brackets around the various terms for a and x, because when you're raising them to powers, you have to raise everything in the bracket to a power. If I look at the next term, the third term, I've got n times n minus 1, a to the n minus 2, x to the 2 all over factorial 2. So looking at my number work here, that gives me 4 times n minus 1, 4 minus 1, multiplied by 3x, which is the a to the power of n minus 2, 4 minus 2, multiplied by the x squared. X is minus 2y, and that's squared, and that's over factorial 2 is 1 times 2. Going to my fourth term here, this one here I'm going to look at, I've now got 4, which is the n, times n minus 1, which is 4 minus 1, times n minus 2, which is 4 minus 2, times by a, which is 3x raised to the power of n minus 3, 4 minus 3, multiplied by the x, minus 2y in this case, raised to the power of 3, all divided by factorial 3, which is the 1 times 2 times 3. I'll let you look at the fifth term here on your own. Example 1b continued here. Our problem, don't forget, is the 3x minus 2y all raised to the power of 4. Our a is 3x, x is minus 2y, and our n is equal to 4. I just repeated this line here for convenience. Now what I'm going to do is raise the brackets to their appropriate powers. So taking the first term, I've got 3x to the power of 4. So don't forget 3 to the power of 4 is 81. So that's 81 times x to the 4. Looking at my second term here, I've got plus the 4 times 3x, that's to the power of 3, 4 taken 1 is 3, and that's multiplied by the minus 2y in brackets. Looking at my third term here, I've got 4 multiplied by 4 take away 1, so that's 3, multiplied by 3x to the power 2 this time, 4 take away 2, and then be careful, I've got minus 2y all squared, so minus 2 times minus 2 is plus 4. Okay, so it's 4y squared there over my factorial 2 again. And looking at the next term here, I've got now 4 times 3, 4 take away 1, times 2, 4 take away 2. I've got 3x to the power of 1 now, and don't forget the minus 2y cubed. So minus 2 times minus 2 times minus 2 is minus 8 there. So that's minus 8y cubed over factorial 3, 1 times 2 times 3. I'll let you look at the last term for yourself. Okay, on the next line I get 81x to the 4, the first term, and then I get 4 times 27x cubed. 27 comes from the 3 cubed, so it's 27x cubed. That's multiplied by 2y. I put a negative at the front, notice, so the positive and the negative makes a negative. Next term I get on the top line 4 times 3 times 4, all divided by 2 gives me 24, and in the bracket I get 3x squared, and that becomes 9x squared, and it's all multiplied by the y squared. For the next term, again, be careful with the numbers. On the top line, you've got 4 times 3 times 2 times 3, and that's all divided by the 1 times 2 times 3 on the bottom. So that will give you 12 there. Be careful with that one. And inside the bracket, you've got minus 8y cubed, and all I've done here is taken a negative outside the bracket, and I've got the 8y cubed inside there. So just sort of simplify my numbers slowly, and then plus the 16y to the 4. What you find sometimes with the final terms is often the numerical values cancel, so that 4 times 3 times 2 times 1 cancels with the factorial 4 on the bottom. Anything to the power of 0 and goes to 1. So that's how I end up with 16y to the 4. And then finally, simplifying on the last line here, I get 81x to the 4, and then do my number work on here, minus 216x cubed y plus 216x squared y squared minus 96xy cubed, and plus the 16y to the 4. I'll let you check the figures there for yourself. Just some common errors that sometimes can occur. When writing out the expansion of a plus b, don't forget to include the binomial coefficients, numerical values, in your expansions. When expanding the likes of a plus 2b raised to the power of 5, remember to take powers of the 2, the coefficient, as well as the b. If you've got something like 10a cubed multiplied by 2ab squared, the solution there is 40a to the 5b squared. In other words, you will square the 2 inside the bracket to get 4, and 4 times the 10 is 40. The a to the 5 and the b squared come from the laws of indices. You do not get this expression. Just be careful of that. Also, be careful with negative numbers. If you have something like a minus 2b raised to the power of 5, the terms will be alternating positive and negative in their expansion. So again, be careful of that. Just some general notes relating to the general form of the binomial expansion, the a plus x to the power n. When n is a positive integer, there are n plus 1 terms in the series. So if the power of n is 5, there will be 6 terms in the series. Power of n is 10, there will be 11 terms in the series. And the series is convergent for any value of a and x, as long as you have a positive integer value. If the n is a negative number, a positive fraction or a negative fraction, the series is unending, and there's an infinite number of terms in the series. However, provided that the numerical value of x lies between minus a and plus a, in other words, minus a is less than x but x is less than a, approximate values can be determined to a reasonable degree of accuracy. For x values outside the range, the series cannot be used to find a solution. Question 1a. We're asked to use the binomial series to expand 3 plus x to the power of 7. So I've written the generic expansion here for us, just to recap. So a plus x to the power of n. Now because it's an n value of 7, there will be 8 terms in the series. So first term, second term, third term, fourth term, fifth term, sixth term, seventh term, 8 terms. So 8 terms in our series in this particular expansion. Notice the pattern we've got here, a to the n times a to the n minus 1 times x plus n times n minus 1 a to the n minus 2 x to 2 upon factorial 2 plus n minus 1 n minus 2 a to the n minus 3 x to 3 upon factorial 3, and so it goes on. There's a pattern there that develops. Question 1a continued here. We're expanding 3 plus x to the power of 7. Don't forget, in this case, the first term in our bracket is a, so that's a is equal to 3, and the second term is the x. In this case, x is x. Not always that case, but it is in this particular situation. And n is equal to 7, the power is 7. All I do now is put the values of a, x, and n into the generic equation on the previous slide. So the first term is a to the n, so that becomes 3 to the power of 7. I add to that n times a to the n minus 1 times x. So in this case that will be 7, which is the n. The a is 3, the n is 7, take away 1. That's multiplied by the x, which is x. Plus the next term, I've got n multiplied by n minus 1. So it's 7 multiplied by 7 minus 1. And that's the a to the power of the n take away 2. And that's x to the power of 2 over factorial 2. My fourth term, I've got n times n minus 1 times n minus 2, so that's 7 times the 6 times the 5, a to the power of n take away 3, x to the power of 3 over factorial 3. In my fifth term, I've got the n multiplied by n minus 1, multiplied by n minus 2, multiplied by n minus 3, multiplied by a to the power of 7 take away 4, multiplied by x to the power of 4 over factorial 4. And so it goes on, repeating that pattern. I'll let you consider the other terms in this series. Okay, question 1a continued. We've got 3 plus x all raised to the power of 7 here. So my expression now simplifies to 3 to the power of 7 for the first term, plus 7 times 3 to the power of 6 times x to the power of 1, plus 7 times 6, 3 to the power of 5 times x to the power of 2 over factorial 2, 1 times 2, plus 7 times 6 times 5, 3 to the power of 4, x to the power of 3 over factorial 3, plus 7 times 6 times 5 times 4, 3 to the power of 3, x to the power of 4 over factorial 4. And hopefully you can see the pattern that's developing. So the next term would be 7 times 6 times 5 times 4 times 3, and it would be 3 to the power of 2, x to the power of 5 over factorial 5. And each time, notice the power is always adding up to 7. Starts with the 3 to the 7, then 3 to the 6 x to the 1, then 3 to the 5 x to the 2, then 3 to the 4 x to the 3. So the powers always add up to 7. They're increasing as you go from the x values from left to right, but decreasing on the number 3 as you go from left to right. I'll let you look at these two terms here for yourself, see if you understand the way they evolve. What you do sometimes find with these kind of calculations, numbers on the top will cancel with numbers on the bottom. For example, if you take the third term, you could cancel the 6 with the 2 to give you 3, slight simplification there. Here you could cancel the 2 times the 3 with the 6, so you get 1 on top, 1 on bottom there. Here you've got the 2 times 3 is 6, and you've got a 4, you cancel with the 4, so get some cancelling top and bottom there. The 6th term here, you would cancel the 5 with the 5, the 4 with the 4, and the 3 with the 3. The 2 could go into the 6 to give you 3. With this term here, you can cancel all of these terms on the top with these terms on the bottom. That'll leave you with 21 on the top, 7 times 3. And the final term here, all these numbers on the top cancel with all these numbers on the bottom, so you just end up with x to the 7, because 3 to the power 0 is 1. So the final line here we end up with is 2187 plus 5103x plus 5103x squared plus 2835x cubed plus 945x to the 4 plus 189x to the 5 plus 21x to the 6 plus x to the 7. You see the x are increasing in their powers as you go from left to right. I'll let you check that slide for yourself. Question 2a here, we're asked to use the binomial series to expand 2c minus 1 upon c, or raise to the power of 5. Don't forget our a plus x to the n is our generic form, so a in this case is 2c, and our x is minus 1 upon c, or you could write that as minus c to the minus 1 if you wanted to, and our n, our power, is 5. So using the binomial expansion as before, we're expanding this to the power of 5, so we get a to the n, so that's 2c to the power of 5 in this case, plus n, 5 times a, 2c raised to the power of the n take away 1, 5 take away 1, and that's multiplied by the x value, which is minus 1 upon c. Third term plus the n multiplied by n take away 1, and this becomes the a term to the power of the n take away 2, and then this is the x term raised to the power of 2, all over factorial 2. We're building up our series slowly. Looking at our fourth term, we get plus 5, which is the n multiplied by n take away 1, 5 take away 1, multiplied by n take away 2, 5 take away 2, multiplied by, in this case, the a, which is 2c to the power of the n take away 3, multiplied by the x, minus 1 upon c to the power of 3, over factorial 3. I'll let you look at the other two terms and see how they are developed. Go back to the original generic equation if you need to find how the terms are formed. Question 2a continued. Don't forget we're expanding 2c minus 1 upon c to the power of 5. Now I've laboured this solution in great detail here so you can follow step by step how the series evolves. Do be careful when you're expanding something like 2c to the power of 4. That is actually 16c to the power of 4, or 2c cubed becomes 8c cubed. Just be careful of that kind of expansion there. Again, as before, you'll find some of the numbers nicely cancelled, top and bottom, certainly for the last term. All of those terms there just cancel with all of those terms there. In this case, all of those terms there cancel with all of those terms there. So you'll find that there's some cancelling that can be done should you want to simplify your numerical work. What you should end up with ultimately is 32c to the 5, take away 80c to the 3, plus 80c minus 40c to the minus 1. That's really minus 40 upon c. I've used a negative index there. Plus 10 times c to the minus 3, or 10 over c cubed, and then take away c to the minus 5. Again, that could be take away 1 upon c to the 5. Question 3a here, we're asked to find the fifth term of the expansion 2 minus x to the power 7, but without fully expanding. So I have actually shown the full expansion here, just for reference, but we only need to find the fifth term. And going back to what we discussed in the previous part of the presentation, don't forget in the fifth term, 4 is common. So in other words, on the top I will get 4 numbers, n minus 1, n minus 2, n minus 3, so I've got 4 numbers there. It will be a to the power of n minus 4, x to the 4 upon factorial 4. So without doing the full expansion, I can actually find this term just by knowing that in the fifth term, 1, 2, 3, 4, 5 in the fifth term, 4 is common. Question 3a continued. So I'm just looking at my fifth term here. I've repeated it for convenience here. So n multiplied by n minus 1, multiplied by n minus 2, multiplied by n minus 3, multiplied by a to the n minus 4x to the 4 factorial 4. So in this case, don't forget our a will be 2, our x will be minus x in this case. Be very careful there. X is negative x, and then the n is equal to 7. What we do then is put the values of the a and the x into the expression and then evaluate the final answer. I'll let you look at the numerical work there. Again, be very careful. Minus x to the power 4 will be x to the 4 here, so be careful of that. I'll let you look at the solution and follow it through in your own time. Question 4a here, we're asked to determine the middle term of 4p minus 1 upon 4q, all raised to the power 10. Now again, if we know that 10 is the power, there will be 11 terms, always n plus 1 terms in the series. There will be 11 terms in the series. So the middle term will be the sixth term in this particular case. Okay, so I've laboured this here. I've shown you the full expansion here. So 1, 2, 3, 4, 5, 6. This will be our middle term. We'll have 1, 2, 3, 4, 5 terms either side of it. Okay, but I don't want you to do the full expansion. I'm just showing you where that term is. We will use a simplified approach to find the value of that term. Question 4 continued here. We know from the previous slide that the middle term is the sixth term in our series, and we know that in the sixth term 5 is common. So therefore our term will have 5 numbers multiplied together in the top line. So n multiplied by n minus 1 times n minus 2, n minus 3, n minus 4. Those are our 5 numbers multiplied together. We have a to the n minus 5, x to the 5, all over factorial 5. The expression we're given is 4p take away 1 upon 4q, all raised to the power 10. Don't forget the first term is an a, so a is equal to 4p in this case, and the second term is the x, and x in this case is minus 1 upon 4q. Don't forget that negative. And n is equal to 10, the power is 10. All I do now is put those values into the expression, so don't forget that's the a value there, the 4p, and that's the x value, the minus 1 upon 4q. What I've done on the next line, I've actually taken the negative to the front of the expression because a minus 1 raised to the power of 5 here will still be minus 1. So I've just taken the negative to the front, and then 4 to the power of 5 is 1024. That's like on the bottom line of that fraction, times by q to the power of 5. What I've also done is cancel the 1024, which is here, which is the 4 to the power of 5 here. I've cancelled that with the 1024 on that bottom line there. So just be careful of that in the formatting there. Those have cancelled out. I'll let you look at the rest of the arithmetic here. You should end up with minus 252 p to the 5 times q to the minus 5. Or if you wanted to, minus 252 p to the 5 divided by q to the 5. And here are some tutorial questions for you to attempt. The answers are shown in the square brackets on the right hand side. Here's the bibliography used to help develop this presentation. Some very good reference sources here I would encourage you to look at for further information. I hope this has been of interest to you. Thank you for viewing.